When you think about the entire generative AI revolution, everything from ChatGPT to the most advanced systems we have today, it's kind of wild to think it can all be traced back to a single elegant idea from a paper published back in 2017. Well, it can. Today, we're digging into Attention is All You Need, the game-changing paper from a team at Google that introduced the transformer and, really, changed everything.
For years, this was the billion-dollar question. See, older AI models used to read a sentence pretty much how we do, one word at a time, left to right. And that seems logical, right? But it created a huge problem. By processing language sequentially, the AI could, easily forget the beginning of a long sentence by the time it got to the end. It just couldn't hold on to all that context.
Okay, let's get into this. The main models at the time were called recurrent neural networks, or RNNs, and they were specifically designed to handle sequences, passing information along from one step to the next, almost like a baton in a relay race. But that very design was also its biggest weakness, a critical bottleneck.
As the paper itself puts it, the fundamental constraint of sequential computation remained. Because an RNN had to process word 1 before it could get to word 2, and word 2 before word 3, you just couldn't speed things up by doing the work in parallel. This made training incredibly slow. And worse, like I said, by the time the model reached the end of a long paragraph, it often had a fuzzy memory of what was said at the beginning.
So this really lays out the old world versus the new. On one side, you have the RNNs just kind of plodding along one word after the other, really struggling with that long-range context. And on the other side, you have the transformer's totally radical idea. A model that can look at every single word in a sentence at the exact same time and just instantly grasp the global context.
The team at Google, they didn't just propose a small improvement here. Nope, they proposed a complete paradigm shift. It was a solution so powerful and so concise that they put the whole concept right there in the title of the paper.
I mean, this was such a bold statement. They were basically saying, let's throw out the entire playbook for sequential processing. No more one word at a time. Their new transformer architecture would be built entirely on something called an attention mechanism, which would let the model see and weigh the influence of all the words simultaneously. Okay, so how did they actually pull this off? I mean, how do you give a machine the ability to see an entire sentence all at once? Let's pop the hood and take a look at the brilliant architecture they came up with.
And here it is, the original diagram from the paper. I know it looks a little complicated, but the key is to just focus on the two main halves. You've got the encoder on the left, which reads the sentence, and the decoder on the right, which generates the output. But the real engine, the magic that drives both of these, is that one repeating component you see in the middle, self-attention.
Right, so this is the crucial part. Self-attention basically allows each word to build its own understanding of the sentence by checking out every other word. It calculates like a relevant score. For instance, think of the word bank. Is it a river bank or a money bank? Well, self-attention lets the word bank look at other words like river or cash to figure out exactly what it means in that specific context.
And this is where their next big innovation comes in. They realized that one perspective just wasn't enough, so they created multi-head attention. You can see it on the right. It's kind of like having a whole team of different experts, or heads, analyzing the sentence all at once. So one head might be focusing on grammar, while another is figuring out who did what to whom. By combining all these different views, the model gets a much richer, more complete understanding.
But this brings up a pretty obvious question, right? If you're looking at all the words at once, how does the model know their order? The dog chased the cat means something totally different from the cat chased the dog. The solution is something called positional encoding. Before any of the real processing starts, a unique signal is added to each word. It's a bit of math that essentially stamps it with its position in the sentence. It's a really simple but totally elegant fix.
So, this new architecture, it was beautiful in theory, but the real test is always in the results. And when the team ran their experiments, well, the transformer didn't just perform well, it completely shattered the existing records for both quality and speed. And the hard data here really tells the whole story. This table compares the transformer to the top models of the time on machine translation. So in that middle column, the blue score, that's just the standard for measuring translation quality. The transformer hits 28.4, way higher than any of its competitors. And then look at the training cost on the right. It got that amazing result using a tiny fraction of the computational power. It was better, and it was dramatically cheaper to train. And just to put that into perspective for you, improving a translation score by even a little bit, like a fraction of a point, is a really big deal.
The transformer beat the previous best, which was actually a bunch of models all working together, by over 2 full blue points. In the world of AI research, that's not just a step forward, it's a giant leap.
The shock waves from this paper were felt way beyond just machine translation. You see, the transformer didn't just solve one problem, it gave us a powerful, scalable, and super efficient blueprint for understanding language that would go on to ignite a whole new era of AI.
So why did it win so decisively? Well, by getting rid of that sequential bottleneck, self-attention created a direct highway between any two words in a text, no matter how far apart they were. And that, combined with the fact that it could be massively parallelized, allowed researchers to train models on more data than they ever could before. This architecture became the foundational blueprint for nearly every major language model that followed, including BERT and, of course, the generative pre-trained transformers, the GPTs that we all know today.
The story of the transformer is just such a powerful reminder that sometimes the biggest leaps forward come from questioning our most fundamental assumptions. This paper identified and just completely solved the sequential processing bottleneck. And it leaves us with a really fascinating question. What's the next fundamental constraint that's out there, just waiting to be broken? And what elegant idea is going to be the one to solve it?